So hi, let me say welcome, Jonathan, and I'm going to show you my world via my YouTube posts. This is my YouTube channel, and these are the posts that I have put up here. There are quite a few. I do this using a piece of software called Camtasia. So Camtasia is a software suite for doing professional video editing, and this is their website. There seems to be many versions. If you look on Amazon.com, I've got one called Camtasia Studio, and it's around $200 and change. I'm not sure exactly what it's called. So we take a look at the properties. So it says it's Camtasia 9, Camtasia Studio. So it's Camtasia 9 is what I've got. One uses an external microphone, and mine is Snowball, or the USB adapter, which has cost $69. So this is my current Twitter account. We can brighten it up a little bit. Brightness on here blows my brains out if I get it too bright. This is my Twitter account, which I've had on here for quite a while. And sometimes I post the stuff from my YouTube account on here. Don't have many followers, but a few people log in. And this is useful for following people and seeing what they're doing and getting information. So I've got a lot of things up here. The artificial intelligence gurus are at the bottom. So Dennis Hassabis is the head of DeepMind. Andrew Ng is one of the gods of the field. Andrew Karpathy is a rising star, having written and presented a course at Stanford when he was doing his PhD on computer vision. He's now working for Elon Musk as director of artificial intelligence under Tesla. Nando De Ferris works for DeepMind. He's put out a few courses earlier on in his career. So I follow DeepMind, I follow NVIDIA. OpenAI is the next biggest AI innovator to DeepMind. So these two guys here publish most of the important advances that is going on. I have Fifi Lee was Andrew Karpathy's supervisor at Stanford. She has now gone over to Google to work in their computer vision area, and she still holds an appointment at Stanford. Some other stuff I am interested in. Richard Soch is a specialist in natural language processing. He created a small company after he graduated called MetaMind, and they got bought out by Salesforce, and now he works for Salesforce, and he's probably quite rich. Pieter Abel is on the Berkeley staff. He produces a course on Introduction to Artificial Intelligence, which I've been through, from which the Grid World project comes from. I can't pronounce this guy's name. He does these wonderful 2-minute papers, which are reviews of the top-end articles that are coming out, which we can look at occasionally. Elon Musk. Hanson Robotics. Hanson Robotics is developing a robotic entity, which is just basically a head. Sophia is a head, and she communicates. She doesn't communicate in the sense of how humans communicate, because their algorithms are very script enhanced. So we really don't know what the actual natural language capabilities of an entity like this is, but they are actually developing the head version of a potential robot. The next most important thing to that in here is probably, which they should have on here, Boston Dynamics. We don't have Boston Dynamics on here. Really? I wonder if Boston Dynamics actually put something out. Let me check. So Boston Dynamics is a robotics company owned by Google originally. We'll found them. We'll now follow them. Just click on the follow and you follow them. They were bought up by a Oriental company called SoftBank that has a variety of interests in the area of artificial intelligence. So we'll follow Boston Dynamics because between Boston Dynamics, which develops robotic entities, and they're basically working on quadrupeds right now, and something that OpenAI has done in regard to a hand that can manipulate things, and Hanson Robotics, they're the three current state-of-the-art elements in building a functional robot, which is a ways off as of yet. So that's what I use YouTube for. Sometimes I post on here and sometimes I just follow what people are putting out. If we hit follow, then we get the stream. Oh, sorry, if we hit home, get it right. If we hit home, we get the stream of what's coming out, so I can follow any information that's coming out of there. So we're going to go over to Wikipedia and look what computer science is about, which is a very, very significant subject in its own right. Areas of computer science involve theoretical aspects of computer science, computer systems, which is due to the architecture, and computer applications, of which there are many. So I am in artificial intelligence, so we'll go to artificial intelligence. And we say artificial intelligence, it comes under the broad umbrella of machine learning, which I don't like the name of because this is primarily to do with what is known as classification and regression algorithms, and it has deep learning under it, which I don't think it should be there. Computer vision. Robotics is not really mainstream for this subject area. It just uses coding to enable a robot to do things, so I don't think that's really there. Natural language processing, wherever that may be, is under here. So we have to actually go into machine learning to find deep learning and the other entities. So under machine learning, which is quite a staggering subject matter unto itself, we'll find the other two important things, which are reinforcement learning, which is what I'm doing, reinforcement learning on the one hand, and neural networks, where are they? Deep learning. And deep learning, which is the other area. So I'm working on that interface between these two, which I now combine to give a more enabled subject area called deep reinforcement learning. So arguably the #1 school for computer science is Stanford. It's my go-to. Berkeley #2 for electrical engineering, it's MIT, who do not teach computer science. They teach mixed majors where you have a major in electrical engineering, minor in computer science, or a minor in electrical engineering and a major in computer science. They do not teach pure computer science because it's an engineering school in that regard. So we come along to Stanford and we can go and have a look at what would be like to do a degree in Stanford. So we can click on here, we can click on undergraduate stuff, and we can click on the requirements. So we can go to requirements, and I'm going to let the computer go through this and read it for me, because it's quite a bit, but it's good to go through and get some perspective of what this is all about. So this will take quite a while, but it'll get through it.
The undergraduate CS curriculum and requirements were completely revised for the 2008 to 2009 school year to provide a strong foundation in computer science as well as specialized knowledge through the student's choice of track. The CS curriculum provides knowledge that is applicable across many fields, including many areas of engineering, science, and medicine. The core material of the computer science program has been streamlined into 6 classes that every CS student takes. Students then pick an area that they would like to study in more depth, which becomes their track specialization. The track typically consists of 4 to 5 classes. Finally, students round out their CS curriculum with 2 to 4 elective courses. The electives can be classes from different areas in CS if a student desires more breadth, or they can be additional classes related to the student's track if a student desires more depth. The track-related electives also include courses outside of the CS department for students whose interests cross departmental boundaries and who would like to do interdisciplinary work. For more details about specific classes, check out course ranking sites Carta, old class web pages, and official course evaluations. Course ranking sites have student comments and some official registrar data about course difficulty and instructor quality. Class web pages from previous quarters will often contain handouts and old assignments that can give you a good feel for the class material. Most CS classes are accessible via a Stanford.edu subdomain with the course number as the subdomain. For example, the CS 107 page can be found at cs107.stanford.edu. You can find official course evaluations on Access under Student Greater Than Course and Section Evaluations. When planning a course load, it is a good idea to take into account not only the difficulty of a class but also the type of assignments. Taking 3 classes that all have programming assignments and a large final project is probably not the best idea. Typically, a balanced schedule includes some mix of programming classes and problem set classes. More tips are available on the course load webpage. The information on this page is kept up to date as much as possible, but it is always a good idea to verify that it matches the undergraduate engineering handbook or your specific program sheet since they are the definitive sources of information on these matters. These requirements are set and approved by the School of Engineering. Changes to these requirements must be approved by the School of Engineering Office of Student Affairs in Huang 135 1 quarter prior to a student's last quarter. For most students, this is winter quarter of senior year. More instructions and forums are available at the UG Petitions website. Using AP credit to satisfy math and science requirements must also be approved by the Office of Student Affairs. To receive this approval, take a program sheet and unofficial transcript to Huang 135. The math, science, and engineering fundamentals requirements for the BO computation track differ from those listed here. Please see the BO computation program sheet for specifics. CS majors may use Math 19/20/21 or AP credit to satisfy the calculus requirement. For more information, refer to the calculus sections of the Stanford AP credit chart. The undergraduate curriculum requires 2 CS math classes, Mathematical Foundations of Computing, CS 103, and Introduction to Probability for Computer Scientists, CS 109. These classes give students the necessary mathematical fundamentals to be successful in computer science at Stanford and beyond. 2 additional math electives are required for the CS major. The electives can be any combination of classes from an approved set of courses, listed on the first page of the program sheets. The current electives list includes classes such as the Math 51, CME 100, CME 102 and CME 104. Math 52, Multivariable Calculus, and Math 53, Ordinary Differential Equations, together count as one math elective. Because of significant overlap in the material covered, certain class combinations cannot be counted towards the math requirement. Math 51 and Math 103, Math 103 and Math 113, or CS 157 and Phil 151 may not be used in combination to satisfy the math electives requirement. Students who are applying both Math 51 and Math 52 towards their program sheet, either as math electives or as track requirements, cannot also apply CME 100 to their program sheets. CS majors must take both a mechanics class, Physics 21, Physics 41, Physics 61, and an electricity and magnetism class, Physics 23, Physics 43, Physics 63. Mixing classes from different series is acceptable. Physics labs are not required for the CS major. In general, almost any college-level, first-year physics class that covers mechanics and E&M will be awarded transfer credit and count towards the physics requirement. So if you want to take physics at Foothill College, the local community college, or at home over the summer, that is usually fine. The School of Engineering approves this requirement, so it might be wise to check with them ahead of time if you're planning to do this. AP credit will also satisfy the physics requirement. For more information, refer to the physics sections of the Stanford AP credit chart. The science elective is one or perhaps two classes to bring the total science units to at least 11. The list of approved electives includes the School of Engineering Science electives list, plus Psych 30, Perception, or Psych 55, Cognition and the Brain. A 5 on the AP Chemistry exam will count as 4 units of science elective credit. This year's undergraduate engineering handbook will also have an up-to-date list of classes that can be counted towards the science elective. CS 106X covers the same topics as CS 106B, but with more in-depth coverage and at a faster pace. Note that it is also possible to take CS 106X, rather than CS 106B. After taking CS 106A, it is also strongly recommended that you take CS 106X even if you there had a considerable amount of prior programming experience. Particularly if you do not know C++. This will ensure you have the necessary foundation for more advanced work expected in later CS classes. ANGR 40 is an introductory electronics class taught by the EE department. The class has weekly problem sets, labs, a midterm, and a final. The Engineering Fundamentals elective is another class from the School of Engineering Fundamentals list and includes ANGR 10, Engineering Analysis, ANGR 14, Statics, ANGR 15, Dynamics, ANGR 20, Chemical Engineering, ANGR 25, Bioengineering, ANGR 50, Materials Science, ANGR 60, Engineering Economy, and ANGR 62, Optimization. This year's undergraduate engineering handbook will also have an up-to-date list of classes that can be counted towards the Engineering Fundamentals elective. Effective as of the 2017 to 2018 program sheets, you can now count an additional CS depth course, track or general elective, in place of the second Engineering Fundamentals course. The TIS class is designed to give engineers an understanding of their profession as a social activity. The TIS classes are devoted to exploring issues arising from the interplay of engineering, technology, and society. Any class from the School of Engineering Technology and Society courses list can be counted towards this requirement. This year's undergraduate engineering handbook will also have an up-to-date list of classes that can be counted towards the technology and society requirement. CS 106B introduces students to many fundamental programming concepts and software engineering techniques using the C++ language. The course will focus on teaching problem-solving skills, basic abstract data tips, and recursion. General topics include basic programming methodology, engineering, modularity, documentation, data abstractions, stacks, queues, linked lists, hash tables, binary trees, generics and templates, recursion, procedural, backtracking, searching and sorting, and basic algorithm IC analysis, including big O notation. CS 107 transitions students to programming on the Unix machines. The class aims to teach students about computer systems from the hardware up to the source code. Topics include machine architecture, registers, I/O, basic assembly language, memory models, pointers, memory allocation, data representation, compilation, stack frames, semantic analysis, code generation, and basic concurrency, threading, synchronization. CS 110 will teach students how to build larger-scale systems using operating system and networking abstractions. Topics include processes, threading, context switching, inter-process communication, storage and file management, file systems, virtual memory, networking, sockets, TCP/IP, routing, and an understanding of distributed systems. CS 103 will give students the mathematical foundations necessary for computer science. Topics include proof techniques and logic, induction, sets, functions, and relations, an introduction to formal languages, FAS, NFAS, and regular expressions, context-free grammars, Turing machines, and NP-completeness. CS 109 is designed to teach students material from probability and statistics that is relevant to computer science. Topics include combinatorics, probability theory, conditional probability, and independence, probability distributions, Bayes' theorem, law of large numbers, and the central limit theorem, and hypothesis testing. The class will also cover applications of probability including hashing, data analysis, inference, and an introduction to machine learning. CS 161 gives students the tools to analyze data structures and algorithms. Students will also practice devising algorithms for various problems. These skills are widely applicable, and alumni report CS 161 as one of the most useful classes at Stanford. Topics include algorithm IC complexity analysis, Big O, Omega, Theta, recurrence relations, and the master method. In addition, students learn about several different classes of algorithms and data structures, including randomized algorithms, divide and conquer strategies, greedy algorithms, hashing, heaps, graph algorithms, and search algorithms, including blind and asterisk search. The tracks allow students to develop depth in a particular specialization by taking 4 to 5 courses in a related area. Students must complete the requirements for any one track, which typically includes 1 to 2 gateway classes, 1 to 2 classes form a menu of highly related courses, and then a selection of classes from a list of more broadly related courses. Together, the track plus electives must equal at least 7 classes and 26 units. The current tracks are Artificial Intelligence, Theory, Systems, Human-Computer Interaction, Graphics, Information, Biocomputation, Unspecialized, and Individually Designed. For details about individual tracks and advice for choosing a track, see the tracks page.
So we'll move to the tracks page and look at the area that I'm interested in, artificial intelligence. Hang on a second. So it reads, artificial intelligence includes the study of foundational materials and topics such as logic, probability, statistics, language, and their relationship to several applications. Topics in the area of artificial intelligence concentration include knowledge representation, logical reasoning, robotics, machine learning, probabilistic modeling, and inference, natural language processing, cognition, speech recognition, and synthesis, computer vision, and computational biology. And we can look at that in a little bit more detail. So if we click on the program sheet, we can select that specifically, and that will come up as a PDF file, which is, thank you. There we go. So this, I've scrolled down here. So you can just get into here and look at what is required under artificial intelligence program. And specifically, these are the courses that would be required, and all the data about where the variables are, what electives you can take, their course, basic courses that are being taught. And what have we got down here? There's a whole bunch of other electives, and that's a pretty good tour of where computer science is, and specifically Stanford. Most courses are available one way or another on YouTube. one of my topics for currently going through a bit more detail is probability. There's only one decent one on here. I don't like his presentation format, but he's definitely a god in the field. I've got the book that he's written, and probability is on my agenda to go through. The other topic that's on my agenda is algorithms, which is actually a good topic for you to get into as a means to understanding how Python works. So this gives you specifics, and I bought the book on algorithms, so you just read through the book and then go through how you tackle these problems instead of just wandering through a book on how to code in Python, which one could do to some extent. You need applications, and this is a good course that you'd have to do if you're doing computer science. So this would be a stepping point to kind of find a way into coding and algorithms, which we could get into at some point. David Silver here, who was the program manager over the development of the Alpha Zero Go program. He has a lecture course on reinforcement learning, which I went through in December. It was a titanic nightmare. Eventually I learned a little bit of it, which springboarded me off into Grid World. So this is the course taught by Pieter Abel at Stanford on Introduction to Artificial Intelligence, and which down one of the lectures it covers the area of Grid World. So down in the lecture he covers Grid World, which is a principal topic in the Bible of Introduction to Artificial Intelligence. And this is one of the things I took on. It was a titanic thing to do. It took me many months to get this anywhere near workable, and it doesn't exactly follow it right to the end, but it codes it enough such that it does get this stuff onto the grid. So we can take a look at that briefly. GitHub is a repository website where professionals and amateurs place their work. It's like a cloud's place for parking your work, and the Grid World is in here. I don't know what version I've got up. Let me just take a look, see. So I'm going to upload the latest file, show you how this is done. So from within this directory we go to upload files. We choose the file, which is buried in where? Oh, we have to go find it. Always love doing this. So we're going to go find the file within the Farmer Projects. It's under Artificial Reinforcement Learning. It's under Grid World, and final 6 is the final algorithm. Let's check that's right. We're on final 6. I've just cleaned it up a bit, so we can open that. It'll bring it in here. Commit changes. Where are we? Oh, it's in Grid World. Final 6 is in there now. So, oops, going back to here just a little bit. We'll run this a little bit, and shortly we'll start putting the numbers onto the grid. It's got a there are 2 policies. One is a greedy policy and one is a random policy. and the greedy policy is set to 90% at the beginning, and every time it hits the reset position. So that's what it does. Now from the course, it goes out and color codes all of these, and it sets it up such that it actually gets into an equitable final state, which my code doesn't do. I just wanted to be able to code this. So the purpose of doing this, showing you this, isn't to impress you with any way, shape or form. It's to just show that I started off knowing nothing about programming and coding a long time ago, and I'm totally self-taught. I haven't taken any input from anybody else. And this is this humongous code which I've written. It's my code, it works, and it involves quite a fair amount of different techniques in Python coding. This is all Python. This has taken me probably about 3.5 months to code up. It was quite significant because I didn't really know what I was doing. I had to learn how to code the graphics portion first, and then get into understanding the algorithm, and moving the agent around on the grid as well was another thing I had to kind of find out how to do, and then all the specials with moving it around and collecting the data and so on and so forth. And finally on my birthday I finally got here. It's a lot of work, it's a lot of work, it's a lot of work, and eventually things get solved. Sometimes I could take 6 or 7 hours a day just trying to find how to solve one individual problem, but they get solved and you move forwards, and you don't worry about I can't do. You just sit there and knock your head up against a brick wall until you can do, and that's what I've taught myself how to do. So that is deep reinforcement learning algorithm for Grid World. I previously went through a course, the course given by Andrew Karpathy on the Introduction to Computer Vision and Convolutional Neural Networks, and with another aid somewhere else I learned how to code deep neural networks, which is what I'm currently working on right now. So this project is fiddling around with me trying to learn how to code a chess playing engine. I have a data set here which is supposed to represent a board. The board actually would look like this, with the rook, knight, bishop, queen, king and so on, and the black on the negative and the white and the positive, and I'm trying to put another number on the side of this, having problems with it, so I've moved towards putting all the zeros as nines and trying to get that to work. Don't worry about all this lot. So this is what a deep neural network is. Don't try and understand it or follow it, but involves putting together what is called a forward pass of putting data together with a random number of a randomization of numbers called weights. Then this has to go through a series of what is called backpropagation, which requires some it requires applying partial differential calculus to the forward pass and working out what this stuff should be, and that gives rise to a deep neural network. It's currently running, and this is what happens when it runs. It tries to give me a better number. So actually, the only purpose of this is to say I've got up to the capability of coding deep neural networks, and now the next step is to bring them together, which is what we're trying to do over here. So this, I've shown you some of this. We'll go back and look at it again, because it's interesting. Rid of that, and we'll come over. Now this is Sensor World. It's another version of Grid World. And I need to bring in the reinforcement learning algorithm with the neural network algorithms and put it together in this this is the data, which is the value data on each of the states in Sensor World. Where are we? Two sets of data here are the same because the data, I'll run it in a minute. It just runs around fairly well, and I've got it up to a reasonable level of being able to return the data value closely approximating its target. So that's my next project. When I get around to starting studying and coding again, it will be taking the algorithm from the reinforcement grid world, porting it into here, taking the deep neural networks, porting it into here, and putting them together, which gives you what is called deep Q learning. It's the first adventure that I will have in the area of deep reinforcement learning, which is quite a piece of work. So I think that's quite a lot to go through all at once. I'll chop this up into bits and pieces and send it you in parts and see if you like it, and then I can always give you other presentations, or I'll just send you it as one whole block, and you can have I can then interact with you more usefully via this medium.